In this video, we will continue our discussion on differential equations in economics. This is the fifth video on that very series. So we will learn about the dynamic stability. Let us say we are being given the supply and demand function is, let us say quantity demanded is being given as is C minus BP. Okay, B is the slope, P is the price, QD denotes the quantity demanded. And let us say quantity supplied is also being given as is minus G plus HP. Okay, now initially what will be our equilibrium? So equilibrium condition will be when quantity demanded is equal to quantity supplied, and when we solve this for price we will get P bar, let us say this is the equilibrium price, will be equal to C plus G upon H plus B. Okay, you can check it out, it will come out to be this very thing. I will not solve it here because I have to do lot more work here, okay, to save the space here. Now in the dynamic stability, what we want to find, let us suppose first let us say our initial price, let us say if initial price, let us say if initial price P R I C price, which is denoted by P naught, if it is equal to the equilibrium price P dash. Okay, if initial price is equal to the equilibrium price, the market will clearly be in equilibrium already and we need no dynamic analysis. But what if this initial price P0 is not equal to the P bar, that is the equilibrium price? Then what will happen? And if we also know that this equilibrium price is attainable, then there will be adjustment during which not only the price will change over time, but quantity demanded and quantity supplied will also change because both are the functions of price. Okay, then we can take price and quantity variables as the functions of time, obviously. Okay, now let's assume that, so let's assume that, and let me write it here. Let us say assume that rate of change of price in market is positive linear function function of excess demand. Okay, and mathematically it can be written as dp upon dt, that means rate of change of price over time is a positive function. Let us denote m as any constant. Okay, it is a positive function of excess demand. What is excess demand? That is simply quantity demanded minus quantity supplied. Okay, so let us say we have this very thing, that rate of change of price with respect to time is the positive linear function of excess demand. Okay, and obviously here this m is greater than 0. Now the condition for dynamic price stability, what we need to find out here. Okay, so condition for dynamic stability, so let me write it here. Condition for dynamic stability or price stability, what we need to find out here. Okay, we want to find out under what conditions our PT, okay, under what conditions our uh, PT will converge converge to equilibrium price, that is P bar, as t tends to infinity, time tends to infinite. So we need to find out this, and it can be calculated like this. So let's write this equation again. So we have dp upon dt is equal to m. So in place of qd we have this very function c minus bp. Then we have minus, quantity supplied minus into minus is plus, so we will get here plus G. Then we have minus minus HP. Okay, solving it further, so we will have if I write it in this format, that is M is equal to M, we have C plus G, C plus G, and let's take minus common, then we have again M. Let's write now H plus B. You can see it here, H plus B. I'm not doing all the steps here, you can do it pretty well. P. Okay, now why I am doing this, this is a deliberate attempt here. I want to write it in a standard form. That means what we got here, dp upon dt. Now transpose this here, it will become plus m h plus b, sorry, h plus b, h plus b, p is equal to m c plus g. Okay, why I have done this, simply I want to write it in a standard form, that is in the form of a first order linear ordinary differential equations. And what is the format for that? That is dy upon dt. You can check it into the earlier videos, I have solved that very thing, explained about that rather, plus vy is equal to z. This is our first order linear differential equation, ordinary linear differential equations. Okay, so I was just trying to convert this function, so this function into this form. So here in place of v, we have this very stuff here, this is our v. In place of z, we have this thing. Okay, so this has been converted into this form. Now the solution for this first order linear differential equation is being given by, that is, and I have shown it in the earlier videos, I will not be able to show it here because of the lack of space and time also. Okay, so the solution of this is being given by, that is, we write p t is equal to e raised power minus v dt. Then we have a, which is the constant of integration, arbitrary constant rather. Then we have z e raised power the integral of v dt, then dt. Okay, this is the solution of this ordinary differential equation. Now here, and let me write it here, this e raised power minus v dt times a, this is called, this thing is being called the complementary function, and this e raised power minus v dt times this z e raised power v dt dt. Okay, this thing, if I solve this, it will become this. This is called the particular integral. Okay, so this is called the complementary function, this is called the particular integral. Now this particular integral, it shows us the intertemporal equilibrium level of price. That means when price is being constant over time, this very thing. And this complementary function shows us the deviation from the equilibrium. Our endeavor is, that means for dynamic stability, this yc, this complementary function must approach towards zero as time tends to infinity. So that means we want this very thing equal to zero. Okay, so that as t approaches to infinity, so that we get the dynamic stable thing. Okay, So I was just trying to show it here. So rearranging this again, so we have e raised power, so let me write it here. We have, and how do I write it here? Let me see, e raised power vdt. Okay, so let's write e raised power minus the integral of dt is t, so we are left with vt. Then we have a plus the integral of z e raised power, again integral of v dt will be equal to vt. Okay, then we have dt. Solving it again, it will become e raised power vt, obviously it is minus, then we have a plus, now the integral of e raised power vt here will be equal to, we will have z e raised power vt upon v, because the derivative, the integral of e raised power vt will be equal to e raised power vt upon v. Okay, we are not writing here the constant of integration, because it will be some subsumed in this arbitrary constant. Okay, that means our pt will be equal to a e raised power minus vt plus z upon v. Now let's write the initial condition. Let us say when 8 or 8 t is equal to 0, when t is equal to 0, if t is equal to 0 in this equation, that means p0 will be equal to, if t is equal to 0, so e raised power 0 will be equal to 1, so we will be left with only a here, plus z upon v. Now let us solve this for arbitrary constant, that means our a will be equal to p0 minus z upon v. Just plug this value again in this equation, so we will get pt is equal to, so in place of a we have p0 minus, so in place of z we know that z is equal to this very thing, mh upon h plus b upon v. So m and m will get cancelled, we will be left with h plus b upon c plus g. Sorry, we have z is this, c plus g. Okay, so it happens here. So a, so we have z, in place of z we have c plus g upon h plus b. Okay, here we have m, here we have m and m will get cancelled. I don't have the lot of space here to show that very stuff here. Okay, so this is our this is our a, and then we have e raised power minus our v again is h plus b, h plus b, h plus b, actually it is m h plus b. Okay, let me write here minus m h plus b t. Then we have plus, in place of z again we have this c plus g upon h plus b, m and m will again get cancelled. Again writing in this fashion, pt will be equal to p0, so this is our p dash which we got earlier, this equilibrium price, e raised power minus m h plus b t plus, again this very thing is p bar. Okay, now here you can see this initial price, it is greater than 0. Our equilibrium price, it will be also greater than 0, and this m, it is also greater than 0, we have assumed it earlier. Now the first term here, you can see we have two terms here, this is the first term, this is the second term. This first term on this right hand side will converge to 0. This will be it will converge towards 0 when this t tends to infinity. Okay, so this first term, let me write it here. First term converges towards 0 when t tends to infinity. Okay, so this whole thing is positive here. Okay, what I want to see here, that is when this t approaches or converges towards infinity, so e raised power minus m into infinity, it will become e raised power, let me write it here. We have minus m, I'm just trying to show it here, h plus b. So if it is infinity here, it will become e raised power minus infinity, and e raised power minus infinity is equal to 0. That means the first term will converge towards 0 as t tends to infinity. Then this first term on the RHS will be equal to 0. That means our PT will converge to this equilibrium price. But the condition there, the restriction on the parameters here, you can see this is only possible that this thing will converge to 0 when this h plus b is greater than 0. If this is not greater than 0, so let me write it here. It is possible only, so it is possible only when this h plus b is greater than 0, which implies when h is greater than minus b. Okay, when h is greater than minus b, then this first term on the RHS will equal to 0 as t tends to infinity. Okay, and our dynamic stable condition will be fulfilled. This will happen only when this h plus b is greater than 0. If it is not greater than 0, if it is less than 0, so what will happen here? It will become e raised power minus m minus m. So it will become a negative number. Let us say it is anything minus. So minus into minus will become plus. Okay, so let me write it here. If it is minus m, if it is less than 0, it will become again uh, minus h plus b. Okay, so let's write it in this form. So it will become e raised power plus infinity here. Okay, so e raised power plus infinity is not equal to 0. Then we will not get this first term equal to 0 on the RHS. So only condition, that is when h plus b is greater than 0, then the first term on the RHS is equal to 0. That means this PT will converge to this equilibrium price. But what is this H and B? That means the dynamic stability requires that the slope of supply function should be greater than slope of demand function. Okay, so here you can see h plus b should be greater than 0. Then this first term on the RHS will be equal to 0, and our PT will converge to this equilibrium price. It will occur only when this h plus b is greater than 0. That means h is greater than b. H denotes the slope of supply curve, h, and minus b denotes the slope of demand curve. Okay, as long as supply curve, the slope of supply curve is greater than the demand curve, we will have a dynamic stable equilibrium. Okay, so our model will be dynamically price stable. If it is not the case, then it will not be the dynamically stable here. Okay, so let me show. If I have here the space, one thing, let's draw, let us say this denotes the time, this is P here. So let us say this is our equilibrium price. Okay, so what our endeavor was, let us say this is another function, that is P naught, and here we have also P naught. When P naught, first thing was when P naught was equal to P dash, then we don't need this dynamic analysis. But what happens if P naught is greater than P dash, or P naught is less than P dash? Okay, so if P naught is less than P dash, or P naught is greater than P dash, then there will be adjustments in the prices and quantity demanded and quantity supplied. Okay, then we want this function to vanish as t tends to infinity, so that the dynamic stability is to be achieved. And in this case we have shown that it will occur only when the slope of the supply curve is greater than the slope of demand curve, then we will get the dynamic stability. Okay, and another way of showing it is here, or another case can be when we have both demand and supply functions positively sloped. Okay, this can also be a thing here. Let us say we have this, uh, let us say this is our supply function, and let us say this is our demand function. Okay, we can see we have unusual demand function and usual supply function. This will also have dynamic stable equilibrium, because here you can see slope of supply function is obviously greater than the slope of demand function. This will also tend towards the dynamic stability here. Okay, so I hope I make myself clear in this video. Thank you.